So I'm going to talk about predicting performance of concrete structures using non-linear finite elements. There's a bit of overlap with what Jan's been saying, but I would say where I'm positioned is kind of midway between the sort of researchy activities that he's certainly been undertaking and regular practitioner work. So this is what I'm going to talk about. A little bit of background, and this is some of this will be pretty basic. And looking at the kind of applications where these tools can really make a difference. And I'm going to skirt across the material models and things like that as well. I'm not going to talk very much about other types of non-linearity. I'm going to focus mainly on materials. I will mention large displacements in one of the examples, but the other forms of non-linear behavior I'm not really going to talk about too much. And then I'm going to talk about a couple of examples. And interestingly, the first one I've decided to pick up is from years ago. And it was at the back end of a very large bridge assessment program, so it sort of fits in with what Steve was saying about his early days and early experiences. The second one is actually it's about serviceability and building things and making things simple in something that's actually really complex. So, well, the challenge, I mean, I suppose more than any other frequently used structural material, representation is always associated with approximation. I think that's fair to say with reinforced or pre-stressed concrete structures, and the challenge to assess and design is to pitch the accuracy and complexity of the analysis so that some benefit is achieved in the overall design or structural assessment, and whilst maintaining required levels of reliability. This is definitely not for a regular design, not yet anyway. There isn't a sort of non-linear button that you press in some of these design engines and, hey presto, you get more results. It does require a deep understanding, and in fact, that's my, I suppose, driver for getting involved in using these tools. Is it can be a virtual test bench, and it does help us understand existing structures and our designs, to improve them and to optimize them. And the kind of applications that we've certainly come across that have shown benefits for using nonlinear concrete FE analysis include things, I suppose, principally structural assessment of existing construction, and I'm going to talk a bit about that. Design of structures not covered well by codes of practice. So we need to be aware of the sort of rules in the codes and how they've been developed, and are we looking at something that really doesn't fit. The other area which is growing, I believe, is in production engineering, really, mass production manufacture of precast concrete components, DFMA and that kind of thing, where it really is useful to pare down the designs and know what's going to happen because there's thousands of them. And also, the design and retrofitting of and strengthening of existing structures. I mean, and actually an extension to that is, exploring defective structures as well. And in the use of, developing new concrete, ultra high performance fiber reinforced concrete, for example, in reinforcement systems. And it's often very useful to perform this kind of work ahead of physical testing where that is necessary, so that the test works and we know how to interpret the results. So the basics. So we've heard about some great stuff from Jan, but here's some basic stuff. It's a composite material, really. Structural concrete is generally a composite material, and this is possibly why there are so many different modeling approaches. Concrete is, non-linear strain. We know all about that. It's brittle in cracking. Its fracture energy and its softening is often largely because of it being attached intimately with reinforcement. It's pseudoplastic behavior in crushing, and when confined, it's pressure dependent, so that you can get higher strengths. And of course, so there are all the things that relate to strength, I suppose, but time dependency, creep and shrinkage, that can get quite complex, changing properties because of maturity. And the second example, I'm going to talk a little bit about that and how we've had to sort of deal with it. And it's the reinforcement that clearly transforms the concrete into this composite material that is so useful for engineering. So material models, this is just a sort of headline summary, really. There's lots of different material models around based on total strain, plasticity, damage constitutive models, reinforcement is generally fairly simple models, actually, based on von Mises yield and that kind of thing. And reinforced concrete, in a way, the material models have to recognize that it's a composite material, and unless you're modeling in great detail, then it has to take account of it in some way. And there's different ways of doing this. Some codes smear the properties of reinforcement into the finite elements themselves, very much on a volumetric basis. So it's sort of macro modeling, and then embedded reinforcement into finite elements. And the two images there, we've got a solid model at the top, and it's not very clear actually, but the bottom shows rebar where it actually is, and then those two are kind of mapped together automatically. That saves us an awful amount of time. And then there's explicit modeling where you're looking at bond and individual bars, and the whole lot's got to be joined up in a sort of continuous way. And as a practitioner, that is normally far too expensive to do because it takes a long time. Right. Okay. So just two more slides here covering modeling concrete in tension. And so there's the tension limit that is particularly important, clearly, and that's when cracks start. And that's driven principally by the principal stress direction and its magnitude. And then, after as Jan has pointed out, after it cracks, then there's a softening process. And for plain concrete, so the graph at the top there, the fracture energy is pretty small, and it cracks, and it's very brittle. For reinforced concrete, it's different depending on how you're modeling it, and so we have to worry about tension stiffening effects, and this really it's extremely important if you're predicting displacement. It's perhaps not so important for strength, and controlling the amount of tension stiffening that you get certainly in a smeared representation. Depends on the area under the curve, basically, and the sort of pseudo fracture energy. And this is actually a tool that gets used to control solutions as well. So the end of the curve, when it softens, relates in some way to the amount of reinforcement and to the ultimate strength of the reinforcement. And there are various empirical sort of rules around that allow you to come up with a number for that. We find often that getting these solutions to converge and to make sure that our internal forces balance our external forces, we often have to increase that value to understand what's happening, and then back down to the point where we're sort of happy that everything's working fine. So this is just a little bit on concrete and compression. The stress states on the right-hand side that Jan talked about, so there's the uniaxial curve at the top there, biaxial behavior, and then in some cases triaxial behavior. So the options really, I suppose, are, I mean, to be honest, in compression, quite often we will simplify the thing and keep the behavior linear, and then check the results. And then that's more efficient computationally. If we do have to consider compressive failures, then the sort of options that are around are fairly classic yield theories like Moore-Coulomb and Drucker-Prager, and with extra modifications to deal with a compressive cap to limit the amount of compression. Another family of these models relates to total strain, and these are quite useful in that they map fairly directly to the sort of uniaxial curves that you will see in codes of practice, and then to account for confined situations and multi-directional stress states. Then there's various parameters that can be introduced to that. And then there's other specialist models around as well, and there's lots to do with seismic engineering and things like this that have all sorts of other adaptations to deal with energy absorption and hysteretic loops and things like that. Okay, so now I'm going to talk about a couple of examples, and this first one is from 20 years ago, and this was the back end of an assessment program. it's Queen Hill Viaduct, which carries the M50. We were actually Category 3 checkers, and the lead consultant carried out their work using Stratton and Tye kind of principles, and it was about the same time that some commercial tools were emerging to allow us to look at non-linear concrete modeling in perhaps more detail than we've been able to before. So this was an ideal opportunity to, as checkers, run this kind of analysis and then compare it with classic solutions. And this particular bridge has lots of half joints in it, which are unusual detail, and I'll show you that in a moment. And there were major concerns as other parts of this structure had serious defects, which in fact resulted in the motorway being closed for a short period of time whilst repairs were organised. We were, as I say, we were commissioned to do the independent check on this a long time ago. So this is just to explain what that half joint looks like. Everything was developed from records, which were pretty good. And obviously some inspection data. So on the left-hand side, we've got the extract from a drawing. On the right-hand side, we've got the geometry model that we put together to help us understand the arrangement. And the concern really is the red boxes. It's a very unusual sort of detail, and embedded steel fabrication into the end of a box girder, a concrete girder. And so this now is our model. Our approach is always to try and keep things simple. And there were several studies going on at this time. There was the green bit there, which is the steel fabrication. Fatigue was the issue there. There was some detailed calculations and assessments done of the red concrete that immediately surrounds the steel fabrication. But then behind that, the end of the reinforced concrete box, that was the bit really that this piece of work was aimed at. And the sort of step change for us, really, and allowed us to do this very efficiently, was the ability to be able to map each reinforcing bar into that finite element model without actually having to deal with the geometries lining up precisely. In other words, reinforcement bars aligning with junctions and nodes in the finite element model, and that saves so much time, and actually aligns nicely now with the sort of BIM technologies that we're using. One of the reasons for looking at this in so much detail, perhaps for the time, was that there were 176 of these joints, and if any one of them failed, then that would be catastrophic. So it was pretty important. So our approach here, well, boundaries are really important. So in a way, the piece of work that for the nonlinear work was a sub-model of a larger model, and the larger model was simply linear, and other checks were done on that using conventional code of practice calculations. But that provided the boundaries for our model, the back of the concrete, and also the target ultimate loads that we're aiming for. I mean, the way we were running this problem, and we do quite often really, is that we have our partial safety material factors in the model. So we're using smaller yield strengths and things like that, and then we run in effect a numerical load test, applying a load where the bearing is in this case, and just ramping it up as far as we can, and then looking at the results to see whether we are achieving the factors of safety that we need. And maybe we've gone way beyond that, and then it helps us understand, the behaviour. And these are the results at the time. I mean, these plots sort of show the age, really, don't they? They're kind of pen plots, really. But so on the left-hand side, that's plotting crack normal strain. So it's not crack widths; it's a sort of smeared approach indicating where cracking is going to occur. If we want to convert that to crack widths, then we have to do some calculations involving crack bandwidths, but this was an ultimate check, and so crack widths perhaps not the objective. On the right hand side, I think it's finished playing now. That's actually the stress in each of the bars. Now, one of the big assumptions that's been made here is apart from the fact that we're smearing things like tension stiffening, but also we're assuming that the reinforcement is bonded to the concrete. And okay, we could add more complexity to the model and consider that too. But what we would do is, in some cases, we can introduce that effect into the model by reducing the stiffness of the reinforcing bars near their ends. And in other cases, then it's a question of checking the results to see whether the rate of change of stress in the bar, for example, would fit within the bond strength criteria. Okay, well, the next example is this is all about time dependency, really. So it's creep and shrinkage are the main issues, and it's about buildability, and it's about serviceability. And many years ago, again, I think it was back in 2008, we got involved in this project. So it's Capitol Gate. It's the world's most leaning tower, according to Guinness Book Records. 35 stories, 160 meters high. It's the centerpiece of the Abu Dhabi National Exhibition Center in UAE. And it leans, I'm not sure how you measure this really, but it leans 18 degrees, which is pretty spectacular. The architect and structural engineer, lead engineer, was RMJM. And we were brought in as specialist support, really. And quite late on, there was already piling, and had a problem. It's a highly organic structure. Every single floor plate is different. Every single node in the diagrid, which is different, and quite complex, really. And this is just, but these are the way the nodes were built, really, and that's a shot from inside the structure. Some of these components are huge. I mean, 800 by 600 rectangular sections, 80 mil thick. Wow. And that's another node. Now this is about halfway up the building. There's an opening to allow light to descend into the structure. The top half of the structure is a hotel, and this gives natural light to all of the rooms. And there the nodes are constructed from circular hollow sections. On the bottom right there, that's just the model, really. But I suppose the key thing here with this building is that normal buildings don't have lateral loads that cause long-term drift. The only sort of things that they might have to resist are things like wind and earthquakes. Capitol Gate is different. It's because of its lean. There's a massive gravity load being applied to this, and the early calculations indicated that it might, the core might lean, as much as 1.2 meters. Now the core on this structure is, originally it was a reinforced concrete core, and then the diagrid around the outside linked with a pretty heavy floor. The driver for our analysis really was to help provide information to build the structure and build that core so that it was vertical to within around 50 millimeters. This is for things like lifts, so that they work, and to understand the sensitivity of the construction to the program. Because creep is key here, it makes a lot of difference depending on how you build it and the rate at which you build it, and where you end up. So the sort of factors that we had to consider, which were time dependent, was the concrete maturity. As we all know, that changes with age. The contractors want to get on with it real quick, so it's often quite soft to start with, and so it's shrinkage and creep of that core is key. But also it gets more complicated. There's creep transfer between the core and the diagrid, and then there's a construction sequence itself. We wanted to be able to review that and understand how that worked. Was there an optimum way of building it? Could we keep up with latest ideas and so on? And we at the very beginning, we knew that the way to deal with this would be to pre-camber. But after we considered all the issues, we felt that what we really needed to do was take some of the risk out of this. Predicting a huge cantilever like this, 160 meters high in reinforced concrete, where it's going to end up after it cracks, is very difficult. With things like that tension stiffening phenomena, which actually varies with creep too, very, very difficult. And so at a very early stage, we decided, well, what we need to do is put vertical pre-stress into this core, not to try and pull it back and to deal with a lean, but to simplify the problem and to sort of convert it to a structure that basically, at least the core, doesn't crack, and also it makes it stiffer, of course. Incidentally, we use Diana for this simulation. Okay, so on the left-hand side, that's a diagram that's sort of showing the various parts of the structure being built. And on the right-hand side, that's just a movie of it going together, really. The red lines are actually the vertical post-tensioning. The diagram on the left illustrates the high-level way the data that's necessary to build this. So the blue curve is the core going together, and then the red curve is, for example, the diagrid, and the purple curve is the facade. And then there's various other things going on in there as well, post-tensioning and things like that. There's literally millions of lines of data in here to do this kind of work. So the complexity in some respects is the data, and the material models are actually not that complex. And then finally, that leads us to running these simulations. So the movie that's going on at the moment is showing you the construction stages as it goes together, and just building it really. So no special attention, just to see what would happen if the contractor just jump formed, followed it with a diagrid. Where do you end up? In a moment, you'll see a shadow, which is where the structure was built, and the way it's deflecting, exaggerated by a factor of 50. Although this does move a lot, say 1.2 meters, something like that. Then using the results from that simulation, we then calculated pre-camber data, and then for each jump of the jump form, the top of the formwork is moved according to that pre-camber. It's three-dimensional, so X, Y, and Z, and basically the principle is build it bent so that it leans straight. I mean, this is regular stuff for some bridge work, although quite often that's two-dimensional. This is the first time that we've done one of these that was truly three-dimensional. And the other thing I should say is that the whole process was automated, because we knew we ran the construction sequence based on the original construction drawings, but we knew once the contractor had started to move on this that he would probably want to change that as his experience grew, or would have other ideas. And so we ran these quite a few times. I should also say that I've made this look a bit simple. There was a lot of intermediate work to understand the way the Crete model worked in particular, and we did testing on literally single elements and 3 stories of this structure, that kind of thing, to assure ourselves that everything was working fine. The other part to this as well, of course, is feedback from the actual construction, and we did develop a specification on how that should be. But actually, we didn't really get much back other than just a few kind of total station geometries. But it worked, and there is a problem, and we don't really know how it was solved because we didn't get feedback from the final construction. But the top floor, as you can see, is a bit slopey, and that was really, there wasn't a way of properly dealing with that. But because it's in the hotel, I imagine you'd never have a place where you could see that, or it would cause a problem. So that sort of brings me to the end, really. But I just wanted to highlight these documents, really, because there is guidance out there on nonlinear concrete modeling and concrete modeling. And so there's the FIB Bulletin 45, which is it covers all sorts of things: linear work, strut and tie work, and so on, and advice on nonlinear analysis. The middle document there, produced by RTD in the Netherlands. This is the first of a series, actually, and it sort of covers general principles, but also then there's a separate volume on the verification of beam models with pre-stress and slabs, and then just a final mention, NAFEMS as well. I mean, NAFEMS doesn't really get used or looked at much by our industry, to be honest, but it's pan-industry. I find it fascinating because the sort of people that are involved with NAFEMS are from aeronautics and aerospace and people like that, and you won't see much concrete, but the methods of analysis they use and the finite element modeling is perhaps what we end up doing later. And for example, the solvers that are emerging, increased usage of explicit solvers. I think these have a place in concrete modeling too. We've been using them for about 20 years to model masonry very successfully. And it sort of avoids the issues with convergence. But the downside is that you use you're solving the equations of motion, so that's more intensive than just looking at stiffness. And you have to use time steps that are very, very small, because the principle really is that your time step is so small that it's faster than the time it takes sound to travel across the element, that kind of thing. And the idea is that if you run your time steps that small, then you can extrapolate safely to post-crack behavior, for example. The downside is those kind of simulations always sort of work, but they may not be right. In the past, they were very expensive and slow to run, but that's all changing now because of massive parallelization. Whereas, explicit solvers, which involve, convergence criteria and so on, if you can get that to work, chances are it's a valid solution. That's it. Thanks very much.